Hi, I'm going to give a lecture on advanced deep reinforcement learning for agentic AI in wireless networks. It is based on a review survey paper. So this is published in 2026. So thanks to Vignan University for giving me this valuable opportunity. So let's go to the motivation. The motivation behind this agentic AI in wireless networks is based on the requirement, today's modern world requirement. The next generation wireless networks needs to support billions of connected devices, IoTs, UAVs, unmanned air vehicles, Internet of Things, and autonomous systems. The future wireless networks they operate in dynamic. Dynamic means it's highly changing. Heterogeneous means devices is not same in the network. Some some devices may be mobiles, laptops, uh, cars, and the environment is highly complex. For example, take urban environment. It is highly dense with buildings, trees. So conventional rule-based optimization is used is used in the olden days, but it is insufficient. It's not sufficient for real-time autonomous network management. So what about conventional deep reinforcement learning? So it is better than rule-based optimization. However, it has predefined objectives. Uh, in the context of wireless networks, it may be throughput, latency, energy efficiency. However, DRL lacks high-level reasoning, planning, and intent understanding. User intention has to be understood by the network. And also conventional DRL limited capability to unseen network conditions. For example, suddenly a disaster comes and changing user requirements. So they are unable to adapt to these conditions. So what are the proposed solutions for these limitations of DRL and optimization? Proposed solutions or research direction is agentic AI for AI native 6G networks. So LLMs provide this reasoning, planning, memory, and user intent understanding, uh, which is a limitation of DRL. And we also use DRL in combination with LLMs to make learning adaptive, policy optimization, and real-time decision making. The combination of LLMs and DRL is almost equal to agentic AI. So agentic AI integrates the LLMs and DRLs to build autonomous, intelligent, and self-organizing or managing wireless networks. So this is the vision for AI native 6G networks. Intent driven, user intent driven, autonomous resource allocation. So resources are bandwidth through power and multi-agent collaboration. So each user equipment is treated as an agent and self-healing and self-optimization. So let's go to the next slide. So let's see the evolution of intelligent decision making for wireless networks. Start with traditional optimization, machine learning, deep learning, RL, DRL, and next it is multi-agent, deep reinforcement learning. And LLMs are used to enhance DRL, agentic AI, and AI native 6G networks. So in each technology there are some advantages and also limitations. So traditional optimization is based on linear programming, convex optimization. Okay. Next, after machine learning has arrived, it is based on data driven. The data has to be labeled before giving to the model. In some applications, it is not possible to label the data. Then the model has to extract the features automatically. This is where deep learning is used. So examples are convolution neural networks, recurrent neural networks, graph neural networks for signal and network analysis. Now, what is the limitation? Autonomous control and interpretability. This is the limitation of deep learning. Next we will see RL. So RL is one of the machine learning technique, supervised, unsupervised, and RL. RL learns through interaction with the environment. For example, in industrial wireless network is considered as an environment. So application is environment in terms of RL. So what is the limitation of this RL is scalability. As the number of agents increase in reinforcement learning, the number of sample efficiency, samples mean state actions, next state reward. You know the RL algorithms, deep Q network, proximal policy optimization. Q learning is without deep learning. Next is a deep reinforcement learning, which is a combination of RL reinforcement learning and deep learning. So here DQN should not be there in RL. So deep RL means deep learning plus RL. So DRL limitation, as I discussed in the previous slide, is task specific. It cannot adapt to the unseen scenario. Let's see multi-agent. So DRL is used with single agent. Multi-agent is a system of different agents. Each agent has a neural network which executes a policy. So it is used in UV networks. Okay. Next is LLM enhanced RL. So the limitations of DRL is overcome by LLMs. It understands reason, intent, user intent, understanding. Okay. However, the limitation is computational overhead and integration complexity is difficult. Sometimes you may find it difficult to integrate LLMs with DRL, and the overhead, computational overhead, as you add LLMs increase. Examples, you can use LLMs for state representation. In wireless network, the states are what is the current state of the network. So we will see what is the state representation of a wireless network. Reward design, we will see in the next slides. So finally we arrive at Agentic AI. So Agentic AI is able to plan, memorize, okay, which has a goal. So you need LLMs and DRL for Agentic AI. So finally we arrive at AI native 6G. So it is autonomous, intent-driven network intelligence, future vision. Future vision is we need a breakthrough in reliability, trust, and scalability. So this is the vision of 6G network. So let's go to the limitations of traditional DRL. There is no reasoning, means it learns policies, but however it cannot reason, plan, or explain the decisions that it takes. No intent understanding cannot interpret high-level network objectives or user intent. Reward engineering. What do you mean by reward? It may be a throughput, maximizing throughput, minimizing latency, or multi-objective reward. So reward engineering depends on the scenario application. So alone DRL cannot design these reward functions. So because objectives may be conflicting with constraints. And poor generalization. It cannot generalize to unseen network environments. Again, we need to retrain and all. So we need agentic AI LLMs with DRL to overcome these limitations. So let's see what is AI native intelligent info architecture. How it can be is first you see user intent and goals. What is his intent? User intention is to provide ultra reliable URLLC, ultra reliable low latency connectivity for autonomous networks. So reliability, low latency, energy efficiency, fair access. So these are the user intents and goals. So how these LLMs take these user intent and goals as input, and it reasons by understanding the context, constraints, and intent. Next is planning. Plans by decomposing large goal into small goals, sub goals, and generate high level plans. Knowledge, user domain knowledge, and also past experience. So it also takes LLM also takes network state, user context, service requirements, historical knowledge all as inputs, and gives output to the DRL agent, which the DRL agent encodes the network state, learning policy, decision making, select actions that maximize the long-term reward. Argmax is a mathematical notation we use. We need to select actions which maximize the long-term reward. So these actions, what are the actions in the network? Resource allocation, beamforming, power control, mobility management. So these actions are applied to the environment. That environment can consist of base stations, user vehicles, UAVs, edge devices. Okay. So environment. What is the observation here? So DRL has an observation from the environment, and a DRL agent applies an action on the environment. What is the observation? Here the environment feedback is the observation. Channel state, throughput, latency, reliability, packet loss, energy consumption. These are the observations. Okay, this is how the AI native wireless network intelligence architecture looks like. So let's go to the next slide. So let's see the fundamentals. What is DRL? What is the state? What is observation? The complete description of the environment, wireless environment. What a wireless environment contains, like I said in the previous slide, channel state information. So this environment, queue lengths, traffic arrivals, okay, topology, mobility. So this is a true state. However, practically getting the true state of the environment is very difficult for an agent. So the practically state becomes observation. So MDP model becomes POMDP, partial observable Markov-Decision process. So observations in wireless network are channel state information, signal to noise ratio, latency, traffic load, queue length, received signal strength indicator. Okay. So this is what state and observation. State is not equal to observation. So what is environment wireless communication network? What is a state? Network observations, resource allocation, power control. These are the actions. Reward we either we maximize or minimize. In this scenario, application throughput maximize, minimize latency. Okay. Improve the energy efficiency by minimizing the energy consumption. Quality enhance the quality of service QAS. So policy maps states to the actions. So states will become an action. The states or observations policy maps either states or observations into actions. So CSAS and latency will be mapped to the resource allocation, power control, beamforming, scheduling. So what is your objective? Your objective is to maximize your expected long-term cumulative reward over the time. The available DRL algorithms are value-based, policy-based, actor critic. Okay. So DQN already I mentioned this in the previous slide. Deep Q network, double deep Q network. So different authors has invented these algorithms. These are called as state-of-the-art algorithms. If it is actor critic, so it depends on your whether your actions are discrete or continuous. So these algorithms can be applied depending upon your requirement. For example, I need channel selection and scheduling. Then you need to select this algorithm value based. For example, I want beamforming power control policy based. I want UAV control resource allocation activity. So particular algorithm for particular application. So what is a value based algorithm? It learns a Q value, quality value. For each state action, there is a numerical value. So what next is selects action with maximum expected reward. So best suited for discrete action spaces, discrete, not continuous. Next is policy based. So directly learns the policy. Okay, A is action, S is state. Optimize the actions using policy gradient. Gradient means differentiation, differential operator. That is suitable for continuous action spaces. Continuous action space. Okay. Activity is a combination of 1 and 2. Okay. So let's go to multi-agent. Why single agent is not enough in this today modern world? For example, take a UAV assisted wireless network. Each UAV is treated as an agent. Also, ground terminal is treated as an agent. So modern 5G 6G networks consist of multiple agents that must operate to optimize the overall network performance. So what is the overall network performance? We already given an example. So typical wireless applications are resource allocation, swarm coordination, edge computing, spectrum sharing, network slicing. So algorithms are multi-agent deterministic policy gradient, Q mix, multi-agent proximal policy optimization, value decomposition network. So single agent is not enough. So this is where I worked in during my PhD. So I multi-agent deep reinforcement learning is where my expertise. So in future I am also trying to add LLMs for a better understanding, planning, memorization. So one work push my research towards agentic AI. Okay, DRL in wireless like it's already explained. So let me it's already explained. Let me uh, summarize. So these are the applications of DRL: resource allocation, beamforming, scheduling, routing, power control. Okay, this is already explained in the previous slide. So I'm summarizing where really DRL is used. So the massive MIMO. So without these algorithms, it is difficult to mathematically. These are mathematically intractable. That is why we are using AI, reinforcement learning, DRL, multi-agent DRL. These are the complex equations which are difficult to solve. Next is advanced RL for LLMs. So here we need to understand what is RL for LLMs, LLM and LLMs for DRL. So we use both. We use R reinforcement learning for all LLMs, and also LLMs are used to in combination or integrated with DRL towards agentic AI. So we need RL for LLMs to reduce hallucination, incorrect answers, generate responses that do not match user intent. If you don't post-train, if you don't give post-training, then LLM generates hallucinations, mismatch, user intent mismatch, ignore safety, ethical constraints. So that is why we use RL for LLMs. You see the list of available algorithms that are used to train the LLMs. LLMs, already know ChatGPT, Claude, Gemini, DeepSeek. These are based on LLMs. So without reinforcement learning, the LLM generates hallucinations, mismatch with user intent. Okay, so let's go to the next slide. So let's go to the next slide. LLMs and DRL as intelligent decision making for wireless networks. So in the previous slide we see RL, reinforcement learning for large language models. Now in this slide we will see a large language models plus combination integration with deep reinforcement learning. So if we use LLMs to understand the user intent, which is comes natural language. So the user may give a prompt to the LLMs to reduce latency for emergency services, the disaster scenarios, and improve reliability. So these LLMs reasons and plans based on the user intent. It understands, analyze the context, plans and decompose goals, generate high-level objectives. So these high-level objectives comes from large language models and given as input to the DRL agent. DRL agent executes based on policy or value-based or actor-critical algorithms and executes actions on the environment, which consists of base stations, channel, edge cloud, UAV, IoT environment. And the actions it performs are resource allocation, beamforming, scheduling, routing. So this is the reward. Let's continue from the previous slide. This is LLM enhanced reinforcement learning. In the previous slide I discussed about reinforcement learning for training of LLMs. Now LLM enhanced reinforcement learning. So LLMs are used to convert raw network data into meaningful state information. So what is the raw network data? Channel state information, signal to noise ratio, traffic load, intelligent network state. So these state representations will be converted into meaningful state information. So this representation improves environment understanding using semantic knowledge. So semantic, uh, Professor Shannon explained about semantic communication. So instead of transmitting raw bits, zeros and ones, semantic communication is required in today's in future 6G networks. Semantic means the meaning of the information should be conveyed to the transmitted to the receiver. So next important task is reward design. In some cases the objectives are conflicting with each other. So in those cases reward engineering or reward function design is difficult. So for that purpose LLMs are used. For example, prioritize emergency services during disaster scenario. So in those, for example, during COVID, emergency travel is only allowed, and non-essential travel is restricted. So in those scenario, disaster scenario, emergency services will be given high priority rather than entertainment services. In normal scenarios, entertainment services take more bandwidth traffic. It has more traffic. For example, YouTube, TikTok, social media. So when an emergency situation comes, for example a disaster scenario, the agentic AI will give priority to the emergency services. So next is world model. So predict user mobility, channel variation and network congestion. So based on this prediction we can better design the, we can make the intelligent more network more intelligent, sorry. So these models are used to predict user mobility, channel variation and network. Okay, finally decision making. So RL agents are used to take decisions based on an, information from LLMs. So these LLMs are used to enhance RL. Okay, next we'll go to the next slide. So now we arrive at agentic AI. So this combination of LLM and DRL and with some other AI models, uh, we can form an agentic RL which is goal oriented and adaptive for AI native future wireless networks. So the first step is it understands the user intent, user requirement, which is a natural language. So for example, user intent is to make sure ensure reliable connectivity and high throughput for users. So based on this user intent, agentic RL sets a goal. Okay, so here LLM is used to plan, breaks the complex objectives into sub goals and tasks. So goal decomposition. So large goals, big goals will be decomposed into small goals. Next, you need to memorize the memory module. In this module, they use external databases plus LLM retriever RAG, retriever augmented RAG. So stores experiences and context for future use. So these experiences, for example, it agentic AI response better, gives better response to unseen scenarios. So if these scenarios, unseen scenarios, once experienced, it will be stored. Third is multimodality. So agentic or in agentic AI based networks, the data is as multimodality. It can be text, uh, images, videos. Okay, it needs to deal with multimodal data. The fourth step is tools. So LLM decides. So it user invokes external tools, APIs, and network functions. Here also LLM is large language models are used as a tools to decide. Finally, policy adaptation. Policy adaptation is done by a DRL agent. So these are the five functions. You can call it five functions of agentic agentic RL. So it reasons, plan, act, learn, adapt. So this is how wireless networks become autonomous using agentic RL. So, so wireless environment may consist of UAVs, user devices, base stations, vehicles, IoTs, edge cloud, network infrastructure. So the applications is network management, autonomous network management, RAN optimization and resource allocation, multi unmanned air vehicle coordination, network slicing and service orchestration, edge intelligence, offloading, and AI native 6G networks. So let's see the wireless for specific application. What are the reinforcement learning algorithms are used? PPO, proximal policy optimization, is used for resource allocation and beamforming. Next, DPO is used for QA, quality of experience optimization and network slicing. GRPO, self-organizing network parameter tuning and fault recovery. So for each application specific algorithm is used. So what are the available open source frameworks for deep reinforcement learning, large language model enhanced reinforcement learning, and agentic AI? Let's see, these are the open source frameworks developed by researchers. Basically, there is a main focus on training and benchmarking. RLHF, this reinforcement learning based on human feedback. Okay, next is Agentic MARL. So, Ray developed by company called Ray. So, multi-agent reinforcement learning library. So, these are the several available open source frameworks. So I have used PyMARL, which is similar to MARL library in my PhD research. So all the links are available in GitHub. So these frameworks. Let's discuss about the challenges. One of the challenges is scalability. Scalability means as the number of agents increases, uh, state action pairs also increase. So this is one of the issues is scalability. So in a large scale 6G network, there are thousands of agents. So this creates a state action pair, more state action pairs. So also need to store these state action pairs as number of agents increase, scalability also increase. So this is one of the is challenge. Next is foundational models. So integrating large language models and DRL is challenging. Next is explainable AI. It is one of the challenge because explainability improves transparency, interpretability, and trust in AI-driven network decisions. Cross-layer optimization in 6G networks. So I worked on a cross-layer optimization. Recently submitted a paper to journal, SCA journal. So it is difficult. It is challenging and is also required to jointly optimize the physical medium access control layer, network layer, application layer for end-to-end performance. Some applications we need to jointly optimize physical layer and network layer. For example, take bottleneck throughput. Bottleneck means worst link throughput. We need to maximize. So maximize the minimum throughput in all possible links. So by which is a function of SAN or physical layer parameter. So this is called cross layer optimization. So I have worked on this. So next is security and privacy is also one of the challenge. As number of agents increase in 6G network, users increase. We need to protect against adversarial attacks, reward hacking, and ensure secure decision making. So these challenges arises when you try to move to the from more transition from 5G to 6G and also use LLMs. So these challenges should be solved by proposing some efficient algorithms. So let's see the next one: future AI native sixth generation networks. So first, the most important input, the input is user intent based on natural language. What the user wants to achieve. A natural language input, service requirements, higher level goals, and also policies and preferences should be considered as should be taken as user input and should be given as input to the large language models. These LLMs do the reasoning for planning, intent understanding, and also knowledge retrieval by using RAG, retrieval augmented generation, task decomposition, plan generation, context awareness. By integrating LLMs with DRL, policy learning, decision making optimization. So, okay, so the if you integrate LLMs with DRL, the goal agentic AI is able to decompose the goals, large goals into small goals, as we discussed in previous slide. Memorize the experiences and also tool use and multi-agent collaboration. Already these agent capabilities are discussed in previous slides. These A native 6G network ecosystem is used in LEO satellite networks, low Earth orbit, terrestrial UAV networks, edge, cloud, and computing intelligent devices. So these should support high mobility, massive connectivity, ultra reliable, low latency, energy efficiency, security, privacy, and semantic communication. Instead of transmitting only raw bits, zeros, and ones, the message should be conveyed. So this already discussed by the Professor Shannon uh, in the past. So autonomous 6G networks should be self-managing, self-optimizing wireless networks. So the key takeaways are deep reinforcement learning, large language models, and agentic RL, which is a combination of LLMs and DRL. Finally, evolution towards a native 6G. So we started from traditional rule-based optimization to machine learning, ML to deep learning and deep learning and reinforcement learning and LLM enhanced reinforcement learning. Finally, we arrive at a native 6G networks. So these are the main concepts that I have discussed in this lecture. Finally, I would like to thank you. Thanks for giving me this opportunity. Thanks for listening patiently to this lecture, 1 hour lecture, 45 minutes lecture on agentic AI in wireless networks.